In this video, we're going to talk about architectural styles. These styles are high-level patterns for system architectures. However, in software engineering, the term pattern is overloaded, and the term architectural pattern is already used in another context. Before we discuss architectural styles, let's review what an architecture is, namely the high-level view of the structure of the system, which is made up of the software components and the relationships between them. The phrase externally visible properties refers to what components can assume about one another. So it includes things like what functions you can call, what performance you can expect, and what protocols you might need to communicate with a component. In general, it includes everything you need to know to interact with that component. And it includes both functional and non-functional properties. Externally visible properties do not include the implementation of the components. That's something that occurs in the construction phase. There are good reasons for creating an architecture. Pressman emphasizes that the architecture is a design artifact that can be understood by all the stakeholders. By the way, when you hear the word artifact, you can just think work product. Item 2 emphasizes that the architecture should be produced early in the design process, so that if any big design changes need to be made, they can be made earlier rather than later. In item 3, Bass is more or less echoing what Pressman says in item 1, that the architecture should be relatively easy to grasp. Okay, now let's look at a few different architectural styles. Each of these styles includes a set of components and connectors between the components. These styles also define certain system-wide constraints and give semantic models that help the designers to understand the architecture. Here are the styles that we're going to look at: data-centered, data flow, call and return, object-oriented, and layered. This is a data-centered architecture. In this architecture, client software accesses a central repository of data, essentially a database. Now, you don't have to pause the video for this unless you want to, but if I give you 10 seconds, can you give me an example of a system with a data-centered architecture? 10 seconds starting from now. Okay, one answer is just about any e-commerce system, and you could probably extend that to most internet software, since clients are often accessing a central server. There's a variation of this architecture in which the central data store is a blackboard instead of a repository. The difference between a blackboard and a normal repository is that a blackboard sends notifications to clients when data that the client is interested in happens to change. A good example of this would be an email system that pushes emails to your phone whenever you get a new message. A data flow architecture consists of a series of pipes and filters. Filters transform the data, and pipes carry the data from one filter to the next. A key property here is that each filter is completely independent from the other filters. The filters simply accept input, transform it, and output the result. If anyone has ever worked in a Unix environment, they use this architecture all the time when writing shell scripts. Shell scripts are usually small programs that transform data using the existing programs in the operating system. For example, I might want to search all Java files in a directory that contain the word interface and then rename those files by putting a capital I in front of their existing names. If I were to do this in Unix, I would need to write a script that contained the find command, xargs, grep, and move. There's a special case of the data flow architecture that occurs when the data flow degenerates into a single line of transformations. This is called the batch sequential architecture. A good example of batch sequential architecture is a typical compiler, like the Java compiler. A typical compiler will take your code as input. It sends it to a tokenizer that outputs a token stream. The token stream is sent to a parser that outputs a parse tree. The parse tree is sent to an analyzer that outputs an abstract syntax tree. And the abstract syntax tree is sent to a translator that outputs the object code. The call and return architecture is the one found in most non-object-oriented languages. You run the main program and it makes a call to several subprograms, and those subprograms, in turn, make calls to other subprograms. When the subprograms terminate, they transfer control back to the subprograms that called them. These subprograms may be functions, or they may be sets of related functions. This is the kind of architecture you would see in a language like C. And at this point, you may wonder, if this is the architecture that can be applied to all C programs, then why worry about other architectural styles if you're using C? Well, the answer is simple. These styles are not mutually exclusive. Obviously, there's nothing stopping you from implementing a system with a data-centered architecture using the C language. In that case, the system would use both the data-centered architectural style and the call and return architectural style. Okay, one additional note about the call and return architectural style. If the components of the subprograms are distributed across multiple computers, we call this a remote procedure call architecture. This is the object-oriented architectural style. It should be familiar to anyone who has seen a class diagram before. Needless to say, this architectural style fits programs implemented with object-oriented languages. Finally, we have the layered architectural style. This style is common when you have core functionality that you want to implement first, and then you have other functionality that you want to implement in successive iterations. In the way Pressman presents this style, each layer has a specific role. There's a core layer, a utility layer, an application layer, and a user interface layer. The most common kind of system that uses this style is an operating system. Operating systems typically have a kernel, which is the core layer, and then there's a utility layer that contains a lot of small functions like make directory, change directory, move file, delete file. And then there's your application layer where you have components that interface with the applications you install on your operating system. And finally, there's your user interface layer where you have components that interact with the user interface portions of those applications. One important architectural pattern that Pressman does not talk about at length in this chapter is the model view controller pattern. He does mention it, but he discusses it further in the chapter on web app design. However, this pattern is widely used in general. As the name implies, this architecture has three types of components: a model, views, and controllers. The idea here is that there is a single model that holds all the data and the application logic, but you can view the model in any number of ways. Therefore, there are multiple view components. The view is the interface that the user sees. A view has access to the model, and the view determines how information in the model is presented. Each view has a controller component associated with it. The controller takes user input and may update the model based on that input. The kinds of user input the controller accepts is determined by the view. For example, consider a mobile application. The screen provides a view of some data, but it also provides the various buttons and controls that the user interfaces with. When a user presses a button on the screen, that information is sent to the controller, and the controller decides what it means. We'll talk more about the model view controller pattern when we discuss design patterns. And that's it for architectural styles. In the next video, we're going to continue talking about architectural design, and we'll show a simple architecture for the safe home security function.